Great. Thank you. So we are going to talk about Lab 1. The title of the Lab 1 is Small Signal Model Determination. So we are going to talk about the small signal model of BJTs. Just for your information, this lab is a lot, this lab actually covers a lot with the BJTs. So this is the beginning. Now, did you read the last line in lab manual for Lab 1? It's a lab manual, it's not in the syllabus. It says, the uncertainties involved in the measurement will be a limiting factor. That means you will make measurement attempts, real attempts, but may not yield any practical value. So it's like, okay, I made a fair attempt, that's it. You might be expecting value from the data sheet like 200, but you might end up getting 20, who knows, maybe 1000. But the thing is, you made an attempt, or your instrument might not be helping you all the time. For example, if you try to measure a really tiny current, which should be measured by a Q3 high precision equipment, but here you might not be able to get that. So if you don't get that, it's bad luck, but we will make attempts. So this line is actually from, not from me, it's from the lab manual. That's what I'm trying to say. Okay, so it's something like this. You try to break.
He's trying his hardest.
Okay, so we might end up like that, but anyway. So what do we need for the Lab 1? We will need a BJT array CA3046, LVS board, 2200 microfarad capacitors, resistors and wires, etc. As far as I know, we have 3046 in stock, so that shouldn't be a problem. Now, so this is what our circuit should look like, and we should put the IC, the collector current, as 1 milliampere and VCE as 3 volt, and we'll do measurements. So the H parameters in common emitter configuration. H parameter means if you have a transistor, and if you just, I'm not sure what is covered in the text, or if you are taking the course at the same time like you. So the thing is, H parameter means hybrid parameter. It is like if you, instead of considering the transistor as a whole circuit, you kind of break down it in smaller parts. You can say, hey, we'll have some voltage over here, and that voltage is sometimes multiplied here, and that current is here, something like that. So that's what H parameter does. So the H parameter has no meaning. I mean, I can say, okay, H parameter means this. Instead of that, you should look at the definition. Like H of something is given by an equation. If you just look at that equation, that voltage by that current, that's the H parameter. So that's the easier way to understand. Now, let's see how the H parameter works in a common emitter configuration. So this is actually a complete transistor, okay? So for the transistor, this is the base, and this is the collector and emitter. So if we just think about this circuit in terms of the Thevenin, okay, I'm just going blank. Okay, what's that called? Okay, I forgot the exact name of the formula, but the thing is, if you just add the voltage and drops, you kind of end up with the voltage at the end. So VBE here it is HIE times IB here, HREVC, which is a dependent voltage source here. So the VBE equals to this and this, pretty simple. And okay, I remember, it's KVL and KCL. So that's the KVL, and this is the KCL. If you have the IC, it kind of like breaks down in two parts, here and here. So here are the small signal equations, and these are actually the reference numbers. These are actually just from the lab manual, and we are using the RMS or peak to peak, so there is no DC part here because we are talking about small signal all the time. To measure it, what we do is we short C and E by a small reactance. So what happens is we get this. Okay, so it's a very easy thing to imagine. In previous slide we saw some KVL and KCL, and we shorted collector and emitter, which made this term as 0, and from that HIE is VBE over IB and HFE is IC over IB. Okay, so if you say, okay, what is HIE, it's kind of like tough to say in a single word, but if you look at this equation, you can say, okay, the VBE divided by the IB, the base to emitter voltage divided by the base current, is HIE. However, this guy has a much nicer name. We call this guy gain, the transistor gain. The collector current divided by the base current, which is the gain. You can picture a transistor, how it works, like you put some current to the base and some current comes out of the collector, a collector voltage or something like that. So this is the current gain. Okay, now who is responsible for that HIE? We have the ohmic contacts at the base and emitter. There is emitter resistance, depletion region resistance, and base separating base spreading resistance. So these doesn't have any practical calculation or anything related to experiment. This is just for your information. Like, okay, HIE is there, but who is making this term work? I mean, these guys who are contributing to that. So this is just for your information. You don't have to think how base spreading resistance affects HIE. We don't care how, we just know this affects, that's it. It's kind of like a qualitative information instead of quantitative. Okay, so it is reversed. So it's the alternate common emitter H parameter model with all signal reversed. That means previously we had, let's get back to figure 1 and you'll see the difference. Sorry, figure 1.4. Okay, I was going the other way. Here. So this is the figure 1.3. Here you notice the current direction and all the signs. And if we go to the figure 1.4, not here. Oh, sorry for that. Where is here? So here you see the.
You're at 1.3 again.
Okay.
Let's keep going forward. No, you're going backward.
Okay.
You were starting.
So did I paste the same image on both
There you go.
pieces? Okay. Yeah. Here was 1, and here IB, the directions, and you should compare it with this guy. So it's reversed, but however you can do the same measurements and we can get the results. So what are the other parameters? The same equation we can set the IB to 0. Okay, then we end up getting HRE, which is this, HOE, which is IC over VBE. So as you can see, the basic equation is already there. It's the same. In one case, you kill this guy, work with this, get the numbers. In the second case, you kill the IB, set to 0, don't put any base current, and you just solve the numbers. And there are HFE and HIE, which we have to determine with the amplifier configuration. And we'll go over the details in the next slide. Okay, sorry. Here we have the capacitors and see single stage amplifier configuration determining HIE and HFE. Just give me a moment. What was this? Okay, this was HRE, HOE. Okay. That's different. So this HFE, as I mentioned, this is the gain actually. So if we build a single stage amplifier configuration, we can calculate the gain, and that gain is also our HFE. And this is what it looks like. Figure 1.4 was this. So this is the circuit, and when we build the H parameter equivalent, this will be something like this. This is really complicated, and I just went blank, and now I remember. There is a capacitor for C2, and I was thinking, what is the C2? But now I remember, when you have a capacitor or something like this, it actually works as a short for the AC. Okay, so when you do that, your collector current can travel this way short due to AC. So this circuit and the previous circuit, they are the same. And from this you can measure the HIE as VBE over IB. All right. So I should just take a break and say what we are looking at. So it's like you have a transistor, build different circuits, short different parts, make different measurements, and just divide and say, okay, this is my HIE, this is my HFE, this is my HOE, this is HRE, something like that. Now, most of the cases the IB is too small, so from the last slide we can actually run through a lot of equations, and the equations are so big that they don't put here. They're in the appendix section of the lab manual, but however we just look at the final equation what we should be using. Okay, so once we have done all the stuff, we'll just don't have to derive all this. You can look at the equations if you want, but finally HIE is RS over VS VBE minus 1. Now the whole experiment is something like that. Okay, why is it not? Okay, I should hit play. Okay, I paused it. So something like that happens, like you can attacking at the experiment with all the might you have, but it's really tough. So your lab partner shouldn't be acting like this cat anyway. So yeah, that's the end of it. The images are taken from the 312 lab manual, and the cats are from the internet. Where else can I find those cute cats anyway? So tomorrow we are going to meet for that lab. The terrific. I should not terrible. Okay, I'm just mumbling about. The lab is really terrible. Okay, but we are not going to give up. It's tough, but we'll make it. So we should start doing the measurement, and I suggest you to read a little bit from the lab manual, because as I said, it might be okay. You just have the idea like what I was talking to you, but it might not make any sense to you. It's okay. If I were you sitting there, I didn't understand a single word, but you can remember some of my words, and when you start reading that lab manual, it will make sense gradually. Okay, so we are trying to look at the internal working principles of a transistor. So we are building circuits outside, we're shorting this, shorting that, we're taking measurements, we are trying to figure out some H parameters. Some of them will come out to be real nice, some of them will not come to you at all. But that's okay, we are ready for that, right? All right, thank you guys for being here. And any questions? All right, can you please turn the video camera off?